by Mészáros and Pascal Simon about topological superconductors. So here is the plan. It will be mainly on the blackboard, but I have just 2 slides. So the plan is the following. I want first to discuss about Majorana fermions in the context of superconductors, and the main message will be that Majorana fermions are everywhere in superconductors, and those are not the thing that people are searching for. What people are searching for are called Majorana zero modes, and those 2 things are very different. That's the first message. Then I want to come back to the tenfold classification that André mentioned. And this, I will use Xiaogang Wen's word of calling this a textbook superconductor. And later you will see that you can treat superconductor a bit more completely. And that's what he calls real-life superconductor. It means including the gauge field, the coupling to the electromagnetic field seriously. And in between those 2 examples, I will those 2 families, I will treat this example that you already saw with André. And this example, I will first do it as a textbook superconductor, and then we will slowly show what changes if we want to introduce, to include the electromagnetic field. Then we will recap by saying that actually there are 2 families of topological phases of matter. One is made of bands that vary topologically invariant, and that's this classification. And then there is another notion which is called topological order, which has to do with anions, and that's this classification. And the same object, you can see that belonging to this and to that, and we'll see how they merge together. And then I will conclude with the fact that the usual superconductor, the conventional superconductor, they already have topological order. That's an old intuition of Xiaogang Wen, and it was made concrete about 20 years ago. It's not very well known, but it's true. Okay, so the lecture notes, I typed them, so I will make them available. And if there is only one reference that I recommend, it's this lecture notes by Bernevik and Neupert. It's called Topological Superconductivity and Category Theory. I think they gave it several times. And there are even videos if you want to see them without reading. Okay, so let me show again this tenfold classification. This is a bit a summary of what I will tell you today. So André told us about the 10 different classes. Maybe he didn't show the 10 of them, but only a subset of them. And the 10 symmetry classes, they try to put in the same framework all non-interacting gapped fermionic systems. And non-interacting fermions, when they are gapped, there are 2 big families. They can be just insulators, band insulator, or they can be a superconductor in the mean field description. So in the same table, you have topological insulators and you have topological superconductors. And the 10 classes, they come from different symmetries, which are called external symmetries. There are bit symmetries that it's hard to get rid of. One is time reversal symmetry. Another one is particle hole symmetry. Those are the 2 main ones. And they can be either present or absent. But when they are present, you can also distinguish whether they square to +1 or square to -1. So for example, time reversal symmetry, when it's for spinless particle, it squares to 1. But when it's for spin 1/2 particle, it squares to -1. So here, when it's for instance 0, it means time reversal symmetry is absent. Here it means t square equal +1, and here it means t square equal -1. And the same applies to particle hole symmetry. Can be 0, the square can be +1 or -1. So with these 2, you build 9 families, but then there is a 10th family, because when the 2 are when the 2 are absent here and here, you can still have another symmetry, which is roughly the product of the previous 2, which is called sublattice symmetry or chiral symmetry. But as André mentioned, the name chiral is not very good because it has nothing to do with chirality in the sense of having clockwise or anti-clockwise edge state. It just has to do with, typically it has to do with having a bipartite model. Like graphene, you have 2 sublattices and the hopping is only between one sublattice and the other sublattice. And then you have a special symmetry for this type of models. You have an operator that anti-commutes with the Hamiltonian, and the spectrum has the E minus E symmetry. Okay, so we have these 10 classes, and then you have space dimension. You can even start with D equals 0, as Andrei showed. Here, I will focus on one of the VDG classes, so the classes that describe superconductors. And in 2D, and so we will be here, it will be without time reversal symmetry, but with built-in particle hole symmetry, because it's a VDG type Hamiltonian. And we will be in 2D, and therefore the prediction in this table is that there is a topological invariant, which is an integer. So the bulk of these 2D spinless superconductor is characterized by some integer. And we will see that this integer, you can also see it if you put edges to your system and you have a certain number of chiral edge states. Yes?
I'm sorry, could you just clarify what you refer as, well, the PHS symmetry? Well, how do you interpret it when it's +1, -1, or 0?
I don't have a very good answer to that, but actually there is a two-line proof that when you have a anti-unitary operator, which is the case of both stack reversal symmetry and particle hole symmetry, that when, and if you apply it twice, you know you must come back on the same state. Then you say, okay, I come back on the same state, but there could be a phase. And then there is a two-line calculation that shows that this phase is either 0 or pi, which means that this operator square is either +1 or -1. Okay, yeah.
So the 0 refers to
absence of this symmetry.
Okay. The classical vision of superconductivity, you have time reversal symmetry and particle hole symmetry, right? It's not in here.
In the conventional, you mean?
Yeah.
Yes.
And
yes.
Here it would be +1, +1.
Those two have both particle hole and time reversal symmetry.
Those -1 would spin, so it would be the D3 for electrons.
For example, yes. Okay, so those two refers to this table, but then we will see that if on top of looking at the bulk, looking at the edges, we start looking at what happens in the superconducting vortex, there is an even odd effect. So now the Chern number, this Z, matters only modulo 2, whether it's even or odd. Then we will see that the vortex traps or not, or do not trap a Majorana-Diel mode. And next, we will see that if we take seriously those vortices together with the fermions, we can make a theory for anyons. And Kitaev has shown that this theory for anyon now matters modulo 16. So you see there are Z here, then there is a Z mod 2, and then there is a Z mod 16. That's basically what I want to tell you today. And this Z16, it's a sub-classification inside this box. You go into this box, it says there are as many topological superconductor of this family as integers. If you put edges, there are as many chiral edges as this number. But if you just look at the bulk and you look at the anionic property of the excitation, there are only 16 that are different. For example, if nu is equal to 16, it has the same anionic properties as if nu was equal to 0. Okay, and that's my last slide. It's just a remark, but this has always confused me. I just wanted to show you that there are 3 different pictures that illustrate the same thing. Here on the first line, it's a metal. You can either say I have one band that is filled up to here. These are the filled state, these are the empty state. But the same physics you can represent by artificially doubling the degrees of freedom. That's the Nambu or Bogolyubov trick. Then you have one band like this and a reverse band like this. Or you can even just look at the excitation. Those are the electronic excitation and those are the hole excitation. And here you only have the positive energy. Those are just 3 equivalent pictures. In this picture, you think of the microscopic constituent. In this picture, you just think of the excitation. In this picture, you actually artificially double the microscopic objects. And you can do the same with pairing. So maybe this picture is less familiar, but this is also a picture for a superconductor. This is the usual picture where you couple electron hole and you open a gap. And this is the picture where you just look at the positive branch excitation. Okay, so now let's not make a mistake. So,
Projector.
Yes. And should I, no, I can close my computer. Okay, thank you. Yeah, so maybe the first thing I want to say is that when you describe the superconductor in the mean field or Gogolyubov-de Gennes formalism, this is one way of presenting a superconductor, but there is an alternative way which is completely equivalent, no, not preferred, not less preferred, which is Majorana fermions. So when you have a superconductor, mean field description, you can describe everything in terms of Majorana fermions. It's equally valid. It's just a matter of choice. So in this choice, you work with a complex operator, complex fermionic operators. And the thing is that the Hamiltonian contains anomalous C terms or C dagger terms. In this formalism, instead of working with complex operators, you work with real operators, only half the degrees of freedom. But it also has a special kind of symmetry. We'll see. So, yes, maybe the first thing I should say is the following. Let's take a very small example. So A's here are complex operators. So A dagger is different from A, and it creates an electron, and I have a single electronic mode. At this level, particles are conserved. Yes, yeah, so, sorry, that's what I wanted to say. These two formalisms, actually, what they describe are non-interacting fermions. That are number not conserved. We call Q, and actually what they conserve is just fermion parity, fermion number parity. So this is a positive integer, and this one, its eigenvalues are just even or odd. So when you have an Hamiltonian for a superconductor that you treat in the mean field, the only thing that is conserved is fermion parity. And when you have such a problem for non-interacting fermions, an alternative is to phrase it into the Majorana formalism or Majorana fermions. So actually, I started with a bad example. I should at least with two fermionic modes. We do the following example. So, I also want some hopping between the two sides. I want maybe some terms that does not conserve particle number. Like this. So this is a two-side quadratic Hamiltonian for fermions. This is the on-site energy hopping between the two sides, and this is like p-wave pairing, so spinless fermions, and it's paired between neighboring sites. So this Hamiltonian does not conserve particle number because of these two terms, but because the particles are created in pairs or destroyed in pairs, it conserves the parity. So the parity operator here you can write as this. This Hamiltonian commutes with this operator, but it does not commute with this. Now, instead of working with this operator, you can define basically the real and imaginary part of the complex operator. This is what, so I will introduce these guys, which is more or less like 2 times the real part, and C2J like 2 times the imaginary. So this is just like instead of working with complex number, we prefer to work with real and imaginary parts. I will rewrite the Hamiltonian in this formalism, and basically this is just a matter of choice. Some people are actually more used in working in this formalism, and they do all the superconductivity in this formalism. And in this formalism, there are Majorana fermions everywhere. Actually, Majorana fermions are the constituents fermions in a superconductor, because what they are is basically just complex fermions that are only parity conserved and not number conserved. So if you look at the properties of this operator, you can show that, yeah, so first I should mention that they are self-adjoint, they are real. In this sense, also they square to 1. Unlike the complex ones that, of course, square to 0. And they anti-commute. So maybe one important point here is that fermions of this type, they exist in 3 flavors. Maybe I should have started by this. There are Dirac fermions that are the complex fermions. Then there are the Majorana fermions. There are the real fermions, and then there are Weyl fermions that are the chiral fermions. Here, chiral meaning having a definite helicity. So chiral fermions, actually, they do not exist in 2 + 1 dimension, so I'm not insisting too much on this guy. But the other 2, they exist in our 2 + 1 context. Yes?
Just about the fact that the operator are real, I would say they are emission, right? But
yes. No, it's real in the. It's called the real condition, but it's the meaning is this.
Okay. And so the difference with the complex components.
But my point here is that these are just 3 types of fermions. The people that look for Majoranas for years by putting billions, they are not looking for these guys. They are looking for non-abelian anions. They are something different. Yeah. So please have in mind that Majorana fermions are not the same as the Majorana zero mode. So those they have a certain number of degrees of freedom. Those only have half of the degrees of freedom because they are their own. Because of this condition of reality, they are their own antiparticle. So those, for example, they have no electric charge, but they can have a mass. Those can have an electric charge and can have a mass. And those that are chiral, they are necessarily massless, but they can have a charge. So these are the bigger ones. Those have degrees of freedom, and those have the degrees of freedom of the first one as well. So in superconductors, actually, we are playing with these guys. Any BDG superconductor is a system of Majorana fermions. So let's rewrite the Hamiltonian. So it's a little exercise, but I give you the solution. I'm using a strange notation, but that are actually the notation of TIDES, and he's one of the master of the field. And first you think the notations are bad, and then once you've done the calculation, you understand why they are good.
I maybe have a stupid question. Did you just say that the Majorana fermions do not have charge?
Yes. No, yes, they do not have charge, but they can have a mass. They do not need to be at zero energy.
What will be our charge carrier in a superconductor if the fermions don't have charge?
It's the condensate. The condensate, the Cooper pairs are charged. So maybe you are asking about the Bogoliubov quasi-particles. So the Bogoliubov quasi-particles are the complex fermions that are conserved only in parity. And those, they have a charge that depends on their energy. But when you're close to the gap edge, they have zero charge.
Maybe the question is how do you relate like Cooper pairs we see experimentally with Majorana fermion?
So the Cooper pair is for me it's the background. It's the condensate. It's like so there is the condensate. There are pair breaking excitation. Those are the Bogoliubov quasi-particles. And then you also have superconducting vortices. These are the three topological sectors, actually, of the superconductor. So condensate carries charge, no spin if it's an S wave. A Bogoliubov quasi-particle basically carry no charge, but they carry the spin. And then you have the superconducting vortices that have a pi magnetic flux, half a flux quantity.
And what of those are the Majorana fermions?
So the Majorana fermions are just an alternative view of what the Bogoliubov quasi-particles are.
Yeah. Thank you.
Okay, so I'm going to write it like this in a kind of Nambu formalism, but now my Nambu spinner, it's like this. Here I will have a 4x4 matrix, and here is again the Nambu spinner. The notation here by TIDES, maybe you notice you have odd Majorana operator and you have even Majorana operator. For the site number 1, the two Majorana operator, they are going to be C1 and C2. And for the site number 2, they are going to be C3 and C4. But it's not important to keep track of who is even or who is odd, except if you want to remember who comes from which site. So we have 4 Majorana fermions, and before that we had 2 complex fermions, A1 and A2, and if I write the equivalent Nambu spinner, it would be A1, A2, and then the doubling A1 dag, A2 dag. And now I also have a matrix which has some interesting form, but instead of being made of blocks. It's real and anti-symmetric. Maybe here the interesting structure is that this matrix is anti-symmetric. So I'm still following the notation of the masters, but in Andrei's notation, I think it was with an X. Yes. And these guys were called lambdas, lambda hat, and dag of lambda hat. Okay, so now instead of having a Bogoliubov-de Gennes Hamiltonian, you have a Majorana Hamiltonian, and the Majorana Hamiltonian, if you want, it's very particular because it's purely imaginary. It's of even dimension, like a Bogoliubov-de Gennes Hamiltonian, and A is purely is a skew symmetric real matrix. So this matrix is real and skew symmetry. Okay, so maybe let me wrap this up by writing the different. So this was a very small example. You can do all the physics that you like, the Bogoliubov-de Gennes formalism, you can do it with this notation. It's completely equivalent. Just a different way of organizing the degrees of freedom.
Could you give the expression of delta I and delta R?
Yeah, sorry, those are just the real and imaginary part of it. And what's funny with Majorana fermions, look, all the Hamiltonian only looks like hopping. You're hopping between Majorana fermions. Right in component. So this is just hopping because there are no diagonal terms. And the hopping is always with an I or minus I. So when you have a Majorana problem hopping on a lattice, you need to put an arrow to say if when you're hopping, it's going to be a plus or a minus. There is an orientation. If you think it looks like a tight binding model, it is some kind of tight binding model, but the hopping terms, they are all purely imaginary, and you need to say whether it's a plus or minus, so you need to put arrows on your lattice. So all the terms, whether they come from on-site energy, complex fermion hopping, or pairing, it all looks like Majorana fermion hopping. Okay, so you can write it like this, or you can write it with the formalism and the BDG Hamiltonian alternative. And once you diagonalize it, it looks like this. So either you like it in a Bogoliubov-de Gennes form, and then it looks like this. Yeah, so I should specify here now, instead of doing just 2 sites, I do a number of sites which is little n. The matrix is always size 2n, either because of Bogoliubov-de Gennes doubling of the degrees of freedom, or because you separated real and imaginary part, and therefore for each lattice you have 2 Majorana fermions. But then when you look at the modes, you only have them like this. So this is the diagonalized form with complex operator. Those are usually called Bogoliubov quasi-particles, usually noted gamma. But you can also write it, if you prefer, you can also write it in Majorana fermions, but then it looks a bit strange. It looks like this. Sum over n, 1 to n, I, epsilon n, and you have two sets of real operators. Those are like what I called before C1 and C2, but they are the diagonalized form. So those are self-adjoint operators. They satisfy the Majorana type of algebra, and those they satisfy the usual complex fermion algebra. And these guys are the eigenvalues of the single particle problem, the eigenvalues of the Bogoliubov-de Gennes Hamiltonian, or the eigenvalues of this Majorana Hamiltonian. And in both cases, the energies, they come in pairs, epsilon m minus epsilon m. You recover the side of your space, which is 2n. So it's the same trick as the Bogoliubov trick. You have a quadratic Hamiltonians of fermions in second quantization. And in order to solve it, you transform it into a non-interacting fermions with a single particle Hamiltonian that is called the Bogoliubov-de Gennes Hamiltonian. You diagonalize for that Hamiltonian, you obtain single particle modes, and then you fill them. That's the vision like this. And the ground state corresponds to filling nothing. In the language of Majorana fermions, there is no notion of filling. Okay, so maybe this was my first point. Now I want to come back on the tenfold way and concentrate on the class that I want to discuss next. So, what is yes?
So, for example, in the Majorana fermion, how would you describe the ground state, for example?
You mean in this language? Yeah, actually, then I'm a bit stuck because if you really ask me to construct the ground state, I go back to these guys. And why do I need to do this? That's a good question because it forces me to explain something. You can never work in a proper Hilbert space directly with the Majorana fermions because the smallest Hilbert space you can make is of dimension 2, where something happens. And in order to code for a two-dimensional Hilbert space, you need two Majorana fermions to make one complex fermionic mode that is either empty or occupied. So when you really ask me to work in the Hilbert space and everything, I actually go back to these guys. And then the ground state is just the state that is annihilated by all these annihilation operators. Yeah, that's an important point. A single Majorana fermion, it codes for no Hilbert space. You cannot write a Hilbert space. You need to pair two of them, to put them together, rebuild a complex creation and annihilation operator, and the corresponding mode is either empty or occupied.
So what is the physical interpretation of this Majorana fermion? Well, what is the point of having this description?
The point is that it makes clear that the object that you are dealing with, they are fermions that are chargeless, that are their own antiparticle, and that you are dealing with. It's the natural way to describe case where you have fermions that are not conserved in number but just in parity. But it's a bit a matter of taste if you prefer to work with one or the other. Okay, so the tenfold way table that we saw, it's putting together in the same table a band insulator and BDG superconductors that are gapped. And then you have all these classes. So you treat on the same footing something that would be a band insulator with like this, and a Bogoliubov-de superconductor where the gap has been opened because of pairing, and where the two bands are artificial, it's just doubling because of the, actually did it by hand. So when you have such a system with bands, then we learned since the integer quantum Hall effect discovery that in band theory you can attribute topological invariance to bands, and that helps you classify different type of band insulators. If you have a band insulator, you have two bands insulator. Maybe they belong to the same class, maybe they don't, but you cannot tell by just looking at the energy spectrum. You need to look at something more, which is the wave functions. And when you look at the wave function, you can attribute and compute topological invariant that numbers to these bands. The story that I'm telling is that of Chern insulator, for example. There are plenty of such topological invariant, but the most famous is the Chern number. And it's an invariant that you put to each band in your system. If you have a model in which this band has a Chern number of -1 and this band has a Chern number of +1, if your chemical potential is in between, you will have a band insulator which is a Chern insulator that will show a quantum Hall effect, integer quantum Hall effect. The same story goes for BDG superconductor, exactly the same. The only difference is that the origin of the bands is different. Here it's bands because you have several orbitals or sublattices or these kind of things. Here, even without those, you already have two bands because of electron-hole artificial doubling. So maybe this is a bit puzzling, but this is the simplest case where you can have topological superconductor. It's a system where you have no orbitals, no spin, but you have this artificial electron-hole doubling, and still you can define Chern number for this band and a Chern number for that band. And then this is called a topological superconductor. The only difference between this column and that column is that here you conserve particle number, here you only conserve fermion parity, and the corresponding symmetry is called U1 global symmetry. And here it's called only Z global symmetry.
The charge is for
Particle number.
the same, it's charge or not?
No, it's particle number, but I call it Q. And later I will call position P and momentum S. Just to see if you're following. No, it's particle number. Okay, so we can play the same trick of putting, yes?
Considering the superconducting case, what I a bit miss is that for Chern insulator, okay, we have two bands, we can define Chern number. For superconductor, it seems like, if I understood correctly what you have said, is that, okay, take, for example, one band system, then we can go to BDG, then immediately we have two bands, and then use some small pairing, and that's enough. Then in this case, it's enough to define some topological invariant, even though original system had only one true band.
Exactly.
Okay,
that's true. That's the trick of actually superconducting Hamiltonian. It's not really non-interacting fermions. It's mean field treatment of interaction, and the way to transform it into single particle Hamiltonian is by making this doubling between electron and hole, and they are coupled by the pairing, and then you end up having something that looks like two bands, and the corresponding Nambu spinner, it has two components, just like here. So all the things you do here, Berry curvature, etc., you can do here exactly the same. Because you have this Okay, so I want to, in the following, to concentrate on the simplest case, the case that are only precisely the case that we mentioned. So this case is the case of 2D Px plus I Py superconductor. So it belongs to the D class, and that should have a topological invariant which is the Z.
I lost you when you said, so the particle number is conserved and U1 global, what does that mean?
That's the name of the conserved quantity, and that's the name of the symmetry.
And it's not continuous rotation, no, nothing to do with it.
It's what people would call it's the global gauge that you can perform on the fermionic operators, and this is the reason for conserving a particle number. But I insist on the fact that at this level it's a global symmetry. It's not yet local, so I refrain from calling it gauge symmetry.
You started off with spinless fermions, and so you had this p-type coupling. But you could have also had spin-full fermions and had a local S wave.
Yes.
And you would have the same mechanism.
Yeah, except it's a bit more complicated because you have 4 bands. We need spin up, spin down, particle, electron, and hole. So.
But the Majorana fermions.
Oh yeah, you can do everything also in. So here it's just that I'm taking the simplest example. So the simplest example is this one that André discussed a bit in his lecture and in more detail in the question and answer session of yesterday. So I'm going to recap a few things about that. And we'll see how it works. So this is precisely the case where the doubling is the artificial doubling and still will have some topological invariant, which is a Chern number. So this one, if you want, is the equivalent of the Haldane model of a Chern insulator, except that in this model we need the complex fermions and we have 2 real bands because we have 2 sublattices. It's usually done on the honeycomb lattice on graphene. Here we will have a single band, but we'll have the artificial electron hole doubling. Therefore, we only have half of the degrees of freedom of this problem. In both cases, the invariant will be a Chern number, will be a Z. It's just not the same class. This one, I think, belongs to the A class. It's a class of A class in 2D. That's the quantum Hall effect. This one belongs to the D class because it has one special symmetry, which is the symmetry between upper band and lower band. Maybe this is a bit misleading. I should draw it like this. Here, there is no reason to have a symmetry between E and minus E. Here, it's by construction. You cannot avoid it. Okay, and this model, let me write it in a real space. So I will go on a square lattice. I have some hopping in both the X and Y direction. And really, to get you annoyed, now C are complex fermions. So I'm actually taking the following idea. I'm just following the notation from my notes, but also from the reference where I do the stuff, and the reference are given in the notes so that if you read it, you will recognize it in the notes. So those are complex fermions. This is just hopping on the square lattice. Then there is some chemical potential that I shift in order to have the zero of energy at the bottom of the band of the square lattice. And then there is some pairing. So M plus, oh, sorry. So I want to parallel these terms. M plus 1, C, M, M. Like this. So hopping on a square lattice, so that's just, if you solve just this part, you will obtain the usual band of the square lattice. Chemical potential, just to shift the zero of energy, but actually, instead of putting it, the zero in the middle here, I put it really at the bottom of the square lattice band. And then there is some nearest neighbor pairing, so that's P, wave pairing. But then you have this strange I that's breaking chirality, because here I could put minus I and I will have a different chirality. So this is pairing P wave along the X direction, and this is P wave pairing, but along the Y direction. Now we can use the Bogoliubov-Dejean trick to write this as a fake single particle Hamiltonian. And it will have a 2x2 structure. So the complete Hamiltonian can rewrite like this, where I is the non-spinor having the two components, so C minus P tag, and the Hamiltonian is the following. So actually, there are two steps here. First, I need to Fourier transform, and then I need to write it into this form. And once it's written into this form, yes, right here, about functions of P, and the Bogoliubov-Dejean Hamiltonian, it looks like this. On the diagonal, I have the dispersion relation of the square lattice shifted by this. I will write it. And off diagonal, we have something like this: 2I sine px plus I sine py. And here we have the complex conjugate. And the dispersion relation minus P plus Px is cos Py and shifted, yes, sorry, there's a 2 minus mu minus 40. So this dispersion relation, it's the usual one in the square Brillouin zone. If I draw the equi-energy lines, they look like this. Then you have the Van Hoff singularity, and then like this. And the remarkable points that we'll need are these high symmetry points, which are called trim. There is the center of the Brillouin zone, gamma, and then there is X, that's its own image under the sign of P. It goes here, but that's equivalent. And Y goes here, and M that goes here. Or this corner, or that corner, they are all equivalent. Okay, the dispersion relation looks like this, and now we have pairing, and it's P-wave type of pairing, because the pairing term is momentum dependent, and it has some chirality because of the I here. If you look at the expression close to gamma, so to the center of the Brillouin zone. On the diagonal, it's just p squared over 2m minus mu, minus p squared over 2m plus mu. And here it becomes 2I delta px plus ipy, and minus 2I delta px minus ipy. Now you recognize that this is a lattice version of indeed what px plus ipy superconductor is, and I introduced that effective mass is given by the Hoping T. Okay, so now we have a two-band Hamiltonian, and if you're familiar with topological insulators, you can do everything you like about topological insulators on this Hamiltonian. You just close your eyes and you forget it's a superconductor. So it's a 2 by 2, so you can write it, decompose it onto the Pauli matrices. So you can introduce some H of T scalar, the 3 Pauli matrices. So that's what André was calling capital D. It's like you write the Hamiltonian as a Zeeman Hamiltonian and an effective field in a P space, momentum space. And if we write it here, so okay, actually this I explained in the notes, but I will do it quick here. You can do a gauge transformation on the CP operators, and you can replace delta. You can erase the phase of delta, and you can have a model in which you actually work only with the modulus of delta. This you can do by a gauge transformation. It only works if the superconducting pairing is homogeneous in the system, if it does not depend on phase or. So in this case, this we can rewrite as follows. We have a term proportional to tau z, and we have a term proportional tau x, and we have a term proportional to y. So tau x, tau y, and tau z are the 3 Pauli matrices. So now you see that you can define a topological invariant by looking at the mappings of that start from the square Brillouin zone, and that looks at what this effective magnetic field is doing on the Bloch sphere. Because this effective magnetic field, so you can find the, I should first give the band spectrum. So the band spectrum is actually just given by the modulus plus or minus the modulus of H. So that's plus or minus square root of 4 delta square sine square px plus sine square py plus epsilon 0 square. So this in general is fully gapped. It is a dispersion relation that looks a bit like this. Except at some special point where it becomes gapless. And so these are the bands. That's the negative energy band and the positive energy band. Now we want to attribute topological invariance to this band. And one way to do it is to look at the mappings that goes from the Brillouin zone, which is the torus, that goes onto the Bloch sphere, in which this magnetic field live. Actually, it's not really the magnetic field, it's just its direction that belongs to a Bloch sphere. So you need to write that this vector, it has a norm, which is actually epsilon plus of p times the direction, which is a unit vector, and the unit vector lives on the Bloch sphere. And actually, the mathematics of homotopy groups tell us that such mapping, they are classified by a wrapping number. So here I'm cheating a little bit, but the second homotopy group of the sphere is Z. The second homotopy group of the sphere, it's actually classifying mapping from the sphere to the sphere. Here I'm saying that it's also true from the mappings from the torus to the sphere. Because believe me, it's a subtle point, but the result is true. So what we're asking is when we go over the Brillouin zone, which is a torus, what happens to this unit vector on the Bloch sphere? Does it wrap or not the Bloch sphere? Does it wrap it one time, several times? Does it wrap it in one direction or in the opposite direction? And the wrapping number, it's a integer. And in this context, this integer is actually the same as the Chern number. So we can compute it easily by the following shortcut. So Andrei showed some shortcut yesterday. I'm showing another one. The shortcut is the following. Instead of computing the Berry curvature in the whole of the reciprocal space and integrating, you can have a local version in which you only look at points in the Brillouin zone which are particular, which are the Dirac points. So the spectrum is fully gapped. So in principle, there are no Dirac points. So here I'm taking the following definition of a Dirac point. I will tell you in an instant. But whenever you have a Dirac point, you sum over all Dirac points. Each Dirac point contributes to the Chern number by plus 1/2 or minus 1/2. And you have a sum over Dirac points, and they always come in pairs. So in the end, the Chern number is going to be an integer. And what you need to know for each Dirac point to know whether it contributes with plus 1/2 or minus 1/2, you need to know its chirality or its winding number, whether it's a plus type of Dirac point or a minus type of Dirac point. I will come back on that. And you need to know what is the sign of the mass that actually gaps this Dirac point. So in the present case, the Dirac points, we will define them as following. We will say that they are the points such that hx and hy vanish. We take this as a definition. I will pretend that this guy is not there. And when this guy is not there, there are actually points in the Brillouin zone where the hx term and hy term simultaneously vanish. And those I take as my definition of Dirac point. But because this term is not absent, actually at these points where hx and hy vanish, the third term, hz, is not 0. And this I will call it the mass of my Dirac point. The chirality of the Dirac point will be related to these two functions, hx and hy, and the mass it's related to hz. But it's a matter of convention. You can choose to cancel hy and hz, and that this guy is the mass. It works as well, but the position of the Dirac point is going to be different. Why am I talking about Dirac points? It's because if you look at this Hamiltonian that we expanded close to p equals 0, and in particular, if we look at p really going to 0, then I'm forgetting about these terms compared to mu, and I'm assuming mu is non-zero, then you see that this Hamiltonian is actually, maybe if you're used to it, you will recognize it's a Dirac Hamiltonian. It's linear in P on the off diagonal and it's constant on the diagonal. So this Hamiltonian, if I write it in Dirac form, it looks like this. It's minus 2 delta x tau y plus 3y tau x plus a mass, and the mass here is minus mu times tau z. So this is usually taken to be the velocity of the Dirac fermions, and this is usually taken to be the mass times the velocity squared. But okay, here I'm not really paying attention the difference between the mass and the corresponding energy, because I only care about the sign. So let's see where our Dirac points are. There are actually 4 Dirac points here. I need to cancel the hx and hy term. So I need this guy to be 0 and that guy to be 0. And this happens whenever Py is equal either to 0 or pi, and the same for Px. So actually the 4 points that I highlighted here, there are the points where we have the 4 Dirac points. So I have 4 Dirac points. I just need to find what's their chirality and what's their sign of the mass. The chirality you read from this structure. So for example, this one has a chirality of -1. If it was px tau x plus py tau y, it would be a chirality of +1. It's just the way the Pauli matrices, they rotate when I rotate in p space. Does it look like a vortex or does it look like an anti-vortex? When it's a vortex, it's a chirality of +1. When it's an anti-vortex, it's a chirality of -1. And the mass, so here it's -mu, and at the other interesting point, the mass is given by some combination of mu and t. So here maybe I'm just giving the result. I should have a look at the time. Yeah, so I have 4 Dirac points, gamma, x, y, m. The chiralities are as follows. Here it's -1, +1, +1, -1. And the masses, so this one we saw it's -mu. The other ones, they are, so this one is 4t minus mu. This one is 4t minus mu. And this one is 8t minus mu. If you plug this into this formula, you can find the phase diagram of the model we have been looking at, and it looks like this. That's the chemical potential divided by T. Here it's 0, here is 4, and here is 8. No Chern number when the chemical potential is very negative. Then it jumps to +1, then it jumps to -1, then it jumps back to 0. So when the chemical potential is below 0 or larger than mu, actually, before pairing, we have band insulator. The band of the square lattice is either empty or full, because we have the band of the square lattice is like this. And my convention for energy is that it goes from 0 to 8t. So if the chemical potential is either here or there, we have what's called a strong pairing superconductor, and it has a 0 Chern number here or here. And when we are inside the band, then we have a weak pairing superconductor that can have Chern number +1 or -1, depending whether mu is in the first half of the band or the second half of the band. So this is a chiral topological superconductor. It has a chirality, breaks time reversal symmetry. I didn't show that, but you can check it. So you can check the following, that if you do this, star, this is not equal this. This means it breaks time reversal symmetry. You can also check as an exercise that it has particle hole symmetry. Particle hole symmetry in the present context is just like this. So you can also check this property. And the particle Hall symmetry operator, it's tau x times the complex conjugation. And if you take the square of it, it's the square of this Pauli matrix, and it's indeed +1. So we indeed have a model that has no time reversal symmetry and that has particle Hall symmetry of the type such that the square is +1. So this is indeed the D class. So the prediction is that they should be classified by a Z, and we found it. It's a Chern number or wrapping number in our simple case. In this simple model, we only see 3 values of the Chern number: 0, +1, or -1, 0 again. But in principle, in a more complicated model, we can make higher values of the Chern number. Yes.
There's 2 little questions. Do you need a 1/2 in front of the nu?
Yes.
You have a summation of the Dirac points?
Yes, and there are 4 of them. Yeah,
either are 0 or 2, and
when you have a Dirac point that closes and changes the sign of the mass, it switches from +1/2 to -1/2, so it's by 1.
By 1.
Yes.
But that's why I'm confused. Why I need an extra 1/2 in front?
Yeah, you need it to be an integer.
But, and second comment, I think this exact formula, it exactly matches this method I showed yesterday. If this ray you pick is along the z-axis, I picked along the x.
Oh, okay.
Then I think everything reduces exactly to that. That's the sign of not
okay.
cross.
I didn't recognize it. I wasn't sure it was exactly.
We should check in detail, but it really looks like it matches.
Thanks. Okay, so we have a gapped superconductor. It carries a topological invariant. Yes.
Which one did you say? Can I think about the winding? Is it IG sine of NT, or you said one of them is the winding, but I can't remember.
Oh, KID. It's sometimes called the chirality or the winding. It's actually the topological charge of the Dirac point. If you look at the relative phase between the 2 components of the spinner, it looks like little arrows in the Brillouin zone, and the little arrows either they make a vortex or an anti-vortex. That's this charge, it's the vorticity. Also. Okay, so we have something that looks like an integer quantum Hall effect, except it's in a superconductor. So there is no charge being transported here, because the Bogoliubov quasi-particle, at least when they are close to the gap edge, they carry no charge. But if we have a Chern number, then we expect that, so non-zero Chern number, we expect chiral edge states. So now I'm done with discussing the bulk. I move to edge states. So I imagine having a finite system with the vacuum outside, and I say that if in here it's a nu equal 1 superconductor, and outside it's the vacuum, then I expect that on the boundary somewhere I should have a chiral edge state. So it looks a bit like a quantum Hall effect, but it's actually half of a quantum Hall edge channel, because of the number of degrees of freedom. So it's only like the real part or the imaginary part. So it's called a chiral Majorana edge state. And chiral here means Weil, so it's also known as a Weil-Majorana fermion. It's one of a very rare space dimension, 1D, where you can be both chiral and Majorana. So here it's on the edge, so it's one space dimension. So there is no quantum Hall effect. There is actually a quantized thermal Hall effect. So because of chiral edge channel, heat or energy can be transported, but not charge. And the quantity that quantifies this, the good number, the equivalent of the charm number, but specifically for quantized thermal Hall effect, is called the chiral central charge. And in our case, it's half of the charm number. So chiral Majorana mode like this, it's supposed to have a chiral central charge of 1/2. And just like in the quantum Hall effect, I'm using the analogy. If you have a charm number in the bulk which is larger, if it's nu equal 3, then you expect 3 chiral Majorana modes on the same edge. So there is a bulk edge correspondence. The bulk topological invariant is related to the edge number. Okay, so now I want to make one step further. I want to use this little knowledge about what's happening on the edge to discuss what happens in a vortex. So let's really take seriously the fact that we have a boundary of size L. And it's only moving in one direction. So maybe we would expect that our edge has a dispersion relation like this, with P being the momentum along the edge. And if we really have a finite disk, we expect that this should be quantized with a periodic boundary conditions. So something like this. So if I draw my edge mode, I have a dispersion relation like this. That's if the edge was infinite. But because it's closed and of finite size, I'm expecting to have a mode here, mode here, mode here, mode here. And then at some point, it reaches the bulk. But then I have a problem because you see, I told you from the beginning, in the Bogoliubov-de Gennes formalism or in the Majorana formalism, the Hilbert space, when it's finite, it's always of even dimension. In addition, I always have symmetry between plus E and minus E. So having an isolated E equals 0 level is not possible. This is not possible. It contradicts the Bogoliubov-de Gennes formalism. So the solution here is actually that this ladder is half shifted. So the correct solution, and I'm not proving it, I'm just stating it, there is actually, here it should be n plus 1/2. And this is a pi shift or Berry phase shift that has been computed. People have done the semi-classics of these edge states in the superconductor, and they have shown that indeed there is this shift. And this means that the correct ladder of state, when I have a discrete boundary, it's like this. And now you see every state at positive energy has a partner at negative energy. So the energies I have are like this. N plus 1/2 2 pi V over L with N etc. So now let's see what happens if I introduce, in my system, I introduce a vortex. So a vortex, it's actually not a usual vortex, but it's a vortex in a superconductor. And the vortex in a superconductor, it has the following property, that it carries a half flux quantum. So in natural units, if h bar is 1 and E is 1, this is actually a pi flux.
Sorry, stupid question. So you have these energy levels, which are quantized. But then when you reach the perimeter size, then it goes back to the beginning, right?
Yeah, so
does that mean that the energy levels are degenerate in some way?
So I only draw one branch like this. This is the bulk gap. The superconductor is gapped in the bulk. Because of the edge, I have a mode that lives on the edge, but it only moves in one direction. The other one is missing.
Yes.
And the other thing I'm saying is that because the edge has a finite length, I need to quantize the momentum. It looks like periodic boundary condition. That's what I tried first. But with periodic boundary condition, I encounter a contradiction because I have an isolated mode at zero energy. And this is not permitted in a finite size system of the Bogoliubov-de Gennes type. And then I said the solution is simply that actually it's not like this, but it's shifted by a half. This I just claiming it, I didn't prove it. And I draw the corresponding energy levels here.
So you have a finite number of energy levels.
Yes, at some point they enter the gap and they become.
And then they enter the gap.
They enter the bands.
Yeah, they enter the bands, but it's not that they're going back to the base level.
No. They just become bulk levels. They become bulk Bogoliubov quasi-particles. So those are Bogoliubov quasi-particle, but confined to the edge of the system and that have a current. Yes.
Can I see these states? Maybe a very naive question, but I mean, if there's a state in the gap, is this something that can be measured, or is this some quasi-particle that?
Yeah, so some people are trying to see these states, either to really see them with like an STM or something like that, or they are trying to measure the quantized thermal Hall effect.
Successfully?
The successful experiment I know is in is not in a true superconductor. It's in a fractional quantum Hall system that is supposed to map onto a P plus IPY superconductor. But maybe there are. I'm not very familiar with this literature. Maybe we'll learn about this this afternoon. But there have been claims of seeing these things. I don't know if they still hold on. Okay, so now we introduce a vortex. Because a vortex actually is corresponds to a pi flux, it actually means that it shifts again pi 1/2 the result that we just had. So the edge mode, now they are back to this, shifted twice by flux. So now I do have such a mode at zero energy. But I introduced a vortex, and you know that I need to have an even number of modes. So maybe I do have another zero energy mode, but trapped to the vortex. So let's have a semi-classical view of what a vortex is. We can imagine that a vortex, I make it too big, but a vortex, you can imagine that it's like digging a hole inside. So now I have changed the geometry. I have a normal region again inside the superconductor. Therefore, actually, I have a second boundary. Because I have a second boundary, it means I have a second edge mode, and that has to propagate in this direction because of the chirality of the system. Think of it as being, you can think of this as being a ribbon that has periodic direction in one direction, and that is open boundary condition in the other one, or it's this geometry which is actually Corbino geometry. So the vortex here, it's a bit like a Corbino geometry. I also have a mode here. It's counter propagating with respect to the outer mode, and it has a perimeter which is much smaller. Therefore, I also have another branch like this, now with the opposite chirality. But because the size, the perimeter is much smaller, the spacing between the level is much bigger. So I also have the same spectrum from the vortex, but it should look like this. it has a minus because it has the opposite chirality, and it has an L prime with L prime much smaller than L. So maybe I should use a color. So now I have a second zero energy mode, and I have a ladder, but the spacing in this ladder is much bigger. The blue states are states bound to the vortex, and these states are state bound to the outer boundary. So actually, you can make a detailed calculation of what a vortex does into a superconductor, and indeed it does such a ladder of states. In particular, it does a state at zero energy. So now we have two states at zero energy. We have the one corresponding to n equals 0 on the outer edge, and we have one corresponding to n prime equals 0, and that's on the vortex. And these are the Majorana zero modes. And I have a pair of them come by 2. So what is it, Majorana zero mode? So maybe I like to write it as an equation where you see that the Majorana zero mode is actually a composite object. I will argue that it's indeed a Majorana fermion, but it's at zero energy. And it's bound to a topological defect. The topological defects I'm talking about here, it's either the vortex or the domain wall, which is the boundary of the system. Yes?
I have to ask again because I feel this is important. I thought the zero energy state was not allowed.
So it's not allowed to be alone.
Here it's allowed because you've introduced a vortex and hence a defect.
Yes.
There's two of them.
Yeah, there are
No,
two.
but one, the outer edge one is authorized because you have this additional.
Yes.
But you could directly say that because the vortex is there, you do change the periodic boundary conditions,
yes.
that quantization condition.
Yes.
Because it introduces a branch cut.
Yes.
In the delta.
Yeah, the other way to see is to say that it introduces an additional pi phase shift. I didn't talk about branch cuts for the moment. So I have a pair of them, so it's okay. And what I want you maybe to remember as a message is that the Majorana zero mode, it's a composite object. It's made of these three properties. It's a Majorana fermion, so it's like a Bogoliubov quasi-particle, but it's at zero energy, and it's bound to a topological defect. And it's only moving the combined object that we will see something non-trivial, like abelian behavior, anionic behavior. The Majorana fermion by itself, it's not an anion. It's written, it's a fermion. It has really fermionic statistics, fermionic commutation relation. It has nothing to do with anions. So the anion is it's these three things together, and the topological defect is not something unimportant. It's actually the key player in the story. The anions, if you want, they are the quantum version of the topological defects. So it's very important that it's here in the story. Yes.
For a question, the necessity of introducing the vortex here is due to the fact that our chair number is exactly equal to 1, or like...
No, so I could introduce a vortex in any type of superconductor.
No. What I'm asking is that the necessity to realize the zero mode here is the necessity of introducing the vortex here is to realize exactly the zero mode. Otherwise, it's prohibited.
Yes.
But if the chair number is equal to 2, so we have two parallel edge states at the first place. Can we like map them between different momenta?
So if you have nu equal to 2, you will have two parallel edge modes. and you will also have two Majorana fermions bound to the vortex.
Yep.
But when you have two of these modes at the same spatial location, in general, they can hybridize. When they hybridize, they move to finite energy and they make just together, they make a complex fermion and you are back to the Caroli, De Gennes, Matricon type of states.
Okay.
And then when it's three, you have three Majorana modes bound to the vortex. And with three, two can hybridize, but not the three of them, so one remains. Then you see this even odd effect that if nu is odd, you must have a Majorana zero mode bound to the vortex.
Okay. Okay. Thanks.
Yeah, but never stupid question.
So here you introduce one vortex, but if you introduce a family of vortices,
Yes.
then you'll have all these lines in your diagram here, and all plenty of different states.
Yeah.
You're going to fill in the gap, no? Or
No. Okay. So if you introduce many vortices, so if you introduce many vortices, each time you introduce an extra vortex in a nu equal 1 superconductor, you will add one zero energy mode. But that's mainly those guys. For pedagogical purposes, I show them, but in practice they don't show up. They are already in the bands. So each time you add one vortex and the vortex is well separated one from the other, you add one Majorana zero mode in the system, and the edge of the system, it adapts from switching from periodic to anti-periodic boundary condition to make sure that in total the number of Majorana zero mode is always even. So when you have three vortex inside, they are well separated. You have three Majorana zero mode and you have one on the outer boundary. If you have four vortices in the middle, you have four Majorana zero modes on the vortex and you have none on the boundary. And each time you can understand by adding one magnetic flux of pi, it switches back from periodic to anti-periodic boundary.
I'm sorry, I just don't know how we introduce vortices. Do they arise into external magnetic fields?
Yes, so if you wanted to do it in practice, yes, that's what you would do. You would apply magnetic field.
But shouldn't we then do Earth's substitution and then shift those band gaps like higher or lower?
Okay, so yes, if you look at the microscopics of the vortex, you need to do what you said. You need to solve seriously the Bogoliubov-De Gennes equation in the presence of a magnetic flux tube. Look at the region which is depleted. You will find the vortex. You will have penetration of the normal region, penetration of the magnetic field. It's very complicated physics, vortices actually. But this is not my purpose here. Here I'm just using it as a conceptual tool. But indeed, there is all this physics.
Okay. Yeah, and I also don't really understand why it has to be, why the edge mode bound vertex has to be counter-propagating.
Because imagine that I have a square sample. This is one chirality, it's counterclockwise. And on the opposite edges, it's counterpropagating. Okay. This is precisely what's happening here. If you look at this region here, it's moving like this, and here it's moving like that.
Oh. Okay.
Yeah. Another way to see this one is you can make a ribbon, and then it's known in a ribbon. I'm using my inspiration from quantum Hall effect because I'm more familiar with that case, but it's the same for the superconducting case. So in the ribbon of quantum Hall effect, it's like this. If you make periodic boundary condition, it will make this, and this is actually the same geometry as the cylinder, but the cylinder with one mode which is going like this, and the other mode which is going like this, and this is also the same as the Corbino, with one mode going like this and the other going. Okay, so now we have our second big player in the game. We have the vortices that carry or not Majorana zero mode, and we start to see another classification. Beyond the Chern number, we see that the parity of the Chern number matters. It matters whether nu is odd or even. So let me recap. When I have a vortex, superconducting vortex, if nu is odd, I have a Majorana zero mode. If nu is even, there is no Majorana zero mode. And actually, I have something like this. If this is energy, you have a mode pinned at zero energy. If you have a case like this, you have more something like this. You have two states that are symmetrical at epsilon and minus epsilon. And epsilon is the, if you make a case like this, you have two modes on the edge of your sample. You inject one pi vortex inside. There are two Majorana zero modes, but localized in the same vortex. And they, in principle, unless there is some very strict symmetry, they will hybridize. That's the hybridization, the epsilon, and they will, a gap of epsilon will open. And actually, this physics of bound state with a ladder that is half shifted, because you can have extra states. This is called Caroli-Dejean-Matricon bound state. It's known to exist already in superconductors that are conventional superconductors. And this even odd effect, this Z2 classification, or even odd, it was found by Volovic. Okay, and the last ingredient that I want to add, so we have, I mentioned we have the condensate of Cooper pairs. We have the Bogoliubov quasi-particle. Now we have the vortex. If it's nu equal odd, then it's a Majorana zero mode. And with these three players, I want to see that actually there are cases where this vortex is now I want to take it seriously as an excitation. So basically, that's the move of going from a textbook superconductor to a real space superconductor. Is the electromagnetic field now an actor or just a spectator? So real life superconductor would be one in which electromagnetic field is dynamical, it has its own fluctuation, and the vortices, they can appear spontaneously. They are not just things that you apply from the outside. Here it's dynamical Z2 gauge field. So you remember at the beginning that I mentioned that fermions that are parity conserved, they have a symmetry which is not the usual U1 global symmetry, but it's a Z2 global symmetry, just conservation of parity. If you gauge that symmetry, you need to introduce a corresponding Z2 gauge field. You make it dynamical. Now in your model, you have the fermions and you have the dynamical Z2 gauge field. Then this becomes what's has been called a real-life superconductor. And in a real-life superconductor, you want to treat those three actors on the same footing. You will see that these three actors, there will be our anyons that together they make a correct anyon theory. So let me show you why a Majorana zero mode could be thought to be an anyon. check. Okay, so so anions are exotic quasi-particles that have strange or exotic quantum statistics. As point-like objects, they only exist in 2D, two spatial dimension. I'm not entering into the reason why 3D is different from 2D and from 1D, but if you do, if you dig a little bit into the quantum statistics, you will see that in 3D point-like particles, they can be only fermions or bosons. But in 2D point-like particles, they can be, when you exchange them, they can acquire any phase, and they are called anions. So exchange phase can be anything. Actually, it's not completely true that it's anything. If you make it consistent, it has to be a fraction of pi, but almost anything. In addition, the quantum statistics of the objects in 2D is even richer in the sense that now you have the possibility to what is known as mutual statistics. You can even have phases between things that are distinguishable. So this is known as a self-statistic. Self-statistics. You take two identical objects, you exchange them, and you look at the wave function, whether it picks a sign or not. If it picks no signs, it's called boson. If it picks a pi phase or a minus sign, it's fermions. If it's something else, it's called abelian anions. And then there is a second layer of being exotic, is that on top of having these exchange phase and mutual statistics or mutual phase, you can even have the case where your objects together, they split some internal space. So I will give you an example because that's precisely the example of. So internal phase fractionalization or splitting. And then it's called non-abelian anion. When it's just a phase like this, it's called abelian anion.
Could you remind us of the statistics? Of the exotic quantum statistics that they're following?
So, okay, here I'm just saying the following. The usual quantum statistics in 3D, it's just fermions or bosons. In 2D, it's richer because the corresponding group that you need to analyze is not the permutation group, but it's the braid group. And the braid group, it has irreducible representations that are more complicated than the permutation group in 3D. And these irreducible representations, they can be of two types. Either they have dimension 1, and this is the case of abelian anions, just a phase, or there can be higher dimensional representation, 2D, 2, 3, 4, and those are called non-abelian anions. And what it means is that when I have two non-abelian anions together, they code for a Hilbert space that is an internal Hilbert space that is of dimension 2, 3, 4, but only together. So I'm trying to illustrate on the case of the Majorana zero mode.
But wait, usually, so you either have fermions or bosons, right? And the statistics is either fermionic or boson.
Yeah, or here I'm calling statistics not just the occupation factor, but just having fermions and bosons.
All right.
That when you exchange two identical particles, you go back to the same quantum state up to a phase. That's what I call statistics. Yeah, I should have named it different. So here I'm saying that in 2D you can have abelian anions where you take two indistinguishable objects, you switch them you stay in the same quantum phase, in the same quantum state, but up to a phase that is not 0 or pi, and then it's called abelian onions. And then there are more complicated cases in which when you swap two objects, identical objects, you actually move in a degenerate subspace that is of dimension larger than 1. So you're not even sure to come back to the same quantum state. You're just sure that you stay in the same degenerate Hilbert space. And that's precisely the case of Majorana zero modes, because when I have two of these Majorana zero modes, together they form one complex fermionic mode. You remember from the beginning when I have two Majorana fermionic code for one complex mode that can be empty or occupied. So if I have two vortices in a nu equal 1 superconductor, I have two Majorana zero modes. Together they form one complex fermionic mode that's at 0 energy and that can be either occupied or empty. It means that my many-body ground state is twofold degenerate. And when I exchange their position, I'm not even sure if I'm ending in the same state. I'm just sure that I'm ending in the same twofold degenerate subspace. Therefore, by swapping them, I not only get a phase, maybe I get some unitary transformation, 2x2 matrix. And that's precisely what's non-abelian onions. And that's the case with the Majorana zero mode. So the Majorana zero modes, they have this property that when I have 2n vortices well separated, why do I insist on being well separated? Because they actually, the bound state is exponentially bound, and if they are too close together, they can talk together. So you need to have them well separated to remain strictly at 0 energy. So together, they code for a Hilbert space, a degenerate Hilbert space, or I should say ground state degeneracy, that is actually 2 to the n. Because if I have one pair of Majorana fermion, so just one complex fermionic mode that can be empty or occupied, so it's a two-dimensional space. If I have 2n Majorana zero modes, then I have a ground state degeneracy which is 2 to the n. And if I move the Majorana zero modes while keeping them away one from the other, I remain in my 0 energy ground state. So that's now not it's the energy of the total system, not just the energy of the modes of the Bogoliubov quasi-particles. I stay in this ground state, but maybe I have some complicated transformation among them, some unitary transformation. That's actually what happens. So the mathematical framework that describe anions is not the usual group theory. It's some more sophisticated stuff. It's called modular tensor category, and it has the flavor that it needs to say something about not only braiding, but it needs to say something about fusion. And fusion is precisely needed because we have things that together they code for Hilbert space that is not of dimension 1, but of higher dimension. So I'm just mentioning it's called modular tensor category. It has the following ingredients. You need to specify anion types, and I will show you in, for example. You need to specify fusion rules. What happens when you bring these particles together? And then you need to specify grading or phases or rules, grading rules. Together, you can have a mathematical formalism that makes these things consistent. And it's important because it's showing that some things are possible and some things are not possible. So it allows you to classify what are the good anion theory. So in our case, if I take the nu equal 1 superconductor, my three objects, they are called there is always a trivial object, which is called the vacuum or the ground state. In our case, it's the Cooper pair condensate. The second player is the Bogoliubov quasi-particle or the fermion. And the third player is the vortex, which is traditionally known sigma, written sigma. So vortex, or in our special case, it's a vortex carrying a Majorana fermion, so it's a Majorana zero mode. So I have these three anion types. It's also called three topological sectors. And now what are the fusion rules? So most of them are obvious and are a bit trivial. Like one fusing with anything just gives the object itself. When you have two Bogoliubov quasi-particles, they can annihilate, go back into the condensate. Only parity is conserved, and not fermion number exactly. And then the only non-trivial rule is that when I have two Majorana zero modes, they form together a complex fermionic mode that can be empty, or it can be occupied by one fermion. So maybe you've seen this equation about Majorana zero modes, and it just means that together, two Majorana fermions, they code for one fermionic mode that can be empty or occupied. It's the same statement as saying that when I have two Majorana zero mode, the ground state degeneracy is true. Okay, and when you have such a fusion rule with the plus on the right-hand side, it's called non-abelian. And if you have fusion rules that are only with one, every product you only have one outcome, then it's called abelian. And then you see that maybe group theory would be enough and we would not need to go to tensor categories. Tensor category is just to handle properly the case where you have this fractionalization of the internal space. But you see, it's very interesting stuff with the Majorana zero mode. It's like if you have an internal space of dimension 2, it's a bit like having a spin up and a spin down. But it's not local. You've splitted it in two different places. When the two Majorana zero modes are far away, it's very hard to ask the question, are you occupied or are you empty? But it's also very hard to change the state of the system because the noise or the perturbation would need to act coherently on the two locations. But when you bring them back, you fuse them back together, then they hybridize, and then they can tell you whether they were occupied or unoccupied. Okay, and this now if you do consistently, here I didn't mention, but the braiding rules, they are typically given in terms of two matrices. That I will give an example. They are called S and T, but they have nothing to do with the S and T of scattering theory. This matrix actually is the one that contains all the mutual statistical phases. They tell you what happens when you braid two different anion types. And this one, the T matrix, it's very simple. It's a diagonal matrix, and it only contains the phase of the particle when you exchange them. So it only contains self-statistics. So maybe I should give an example. So if we look at the Ising modular tensor category, which is the relevant one for this type of superconductor, I mentioned the objects are like this. They have quantum dimensions. That's the size of their internal Hilbert space. It's 1 for the vacuum and for the Bogoliubov fermion, and it's actually square root of 2 for the Majorana zero mode, meaning that the correct Hilbert space is only defined when I have 2 of them, and it's of size 2. It's just a nasty way of writing that you need 2 to have an integer Hilbert space. When you have such a quantum dimension which is not integer, it means, which is larger than 1, it means non-abelian. What are the exchange phases? also called self-statistics, or it's also called topological spin or 2D spin. So if we were in 3D, this guy would be either 0 or 1/2, or only integer or half integer, nothing else. If I give these objects for these three things, it's like this. 0 phase for the vacuum, it behaves as a boson. Psi, it's -1. It has a pi phase or a spin 1/2. And this guy has a very non-trivial result. It's actually like this. It's EI pi nu divided by 8. Or if you rewrite it, it's like this. 2 pi divided by 16. And now maybe you see that nu mod 16 is playing some special role in the story. So this is the theory describing the anions of the nu equal 1 superconductor. And there are other modular tensor category describing the case with nu equal 2, nu equal 3, etc. until you reach nu equal 16. Maybe I should write another example. So I will do the toric code modular tensor category. It's the name of this category. It also has objects that you can identify physically. It has a condensate, it has Bogoliubov quasi-particle, it has vortices, but the big difference, it has two different vortices. So the objects that are called like this, and those are two different types of vortices. So those are the superconducting vortices, but we are dealing with a superconductor with a 0 Chern number, or 16, or 32. Okay, let's say it's 0. There are two different types of vortices, because now the vortex, because it's even, it carries a standard Caroli-de Gennes state. So now each vortex by itself can already be occupied or empty. It does not need to pair with another vortex. You remember? I have a vortex. It has it's coding for one non-zero mode. And this fermionic mode, complex fermionic mode, it can be either empty or occupied. If it's an empty vortex, it's called M, this guy. If it's an occupied vortex, it's called E, and you can already say that E can write one of the fusion rules. It's an empty vortex that I fuse with a fermion. So here I have a theory for anions where I still have the condensate, the vortex, and the Bogoliubov quasi-particle, but I have two types of different vortices. And now all the fusion rules, they are actually a billion. So the only non-trivial stuff is this one, this equation that I already wrote several times. This one does not occur for this type of superconductor. So for this type of superconductor, actually the vortices, whether they are occupied or unoccupied, they are their own antiparticle. When I bring two, they go back into the vacuum. And the fermion, you can also write it as fusing an E and an M. But all the equations here, you see, you make a product that there is only one outcome, not a sum of outcomes. So they are all abelians. So here, for this case, if I'm giving the names of the, if I'm giving the quantum dimension and the statistics, it doesn't look very exotic, because we will find that all the anion type, they have a trivial one-dimensional internal space. And what is the statistics? The vacuum, the boson. It's also the case of an occupied or an empty vortex, and only this guy is a fermion. So here it looks like a lot of artillery to describe a case where there are actually no anyons. They only have bosons in one fermion. But actually there is something anionic in this business, is that there is a mutual phase which is non-trivial. That if you take an empty vortex and you go around with a fermion and you make a full loop, you will find that you go back to the initial state but with a -1. And this is not a fermionic -1, because I remind you that quantum statistics, it has to do with the exchange of indistinguishable objects. Here I'm not exchanging indistinguishable objects, I'm taking two distinguishable objects, and I'm not making an exchange, I'm making a full loop of one of them around the other one, and I do get a phase. This does not exist in 3D. In 3D, you take two distinguishable objects, you move one around the other one, it comes back to exactly its own state, and there is no phase. So this non-trivial mutual statistics is the signature that even in the toric code case, which has to do with an ordinary superconductor with zero charm number, I already have an anionic behavior inside. So maybe this brings me to my last point. Yes, I'm already over time. That an ordinary or a conventional superconductor has a topological order. Meaning onions. So maybe here I should pause a second to distinguish two different phases of matter that can be classified using ideas of topology. On the one hand, you have a topological bands, and on the other hand, you have a topological order. The first thing I should say is that this one, okay, so this one is also known as integer topo phases. This one is also known as fractional. This one is sometimes also called symmetry protected topological order. And maybe the thing that's most remarkable is that it has to do with single particle-like bands and topological invariant that you put on bands. For the summary, it's like this. So topological invariance for bands. The prototype being the charm number, but there are other types, for example, winding number, and the existing examples of that are integer quantum Hall effect, maybe a Chern insulator, also quantum spin Hall insulator, Kane and Millermall, etc. And one of them would be our textbook superconductor. If you just treat the fermions, just look at the Bogoliubov-de Gennes bands, Chern numbers on these bands, then it belongs to this family of topological phases of matter. Here I'm only talking about gapped topological phases of matter. The other family is the family where you have anions. So there are several characterizations of these systems. First, that the excitation, they fractionalize some quantum number of the microscopic constituents. And then there are some more subtle characterization, like the fact that the ground state has long-range entanglement, that it has topological entanglement entropy. But maybe if you should remember just one thing is that it has anions inside. This one has topological invariance for bands, but the excitation here, they are more or less the same as the microscopic constituent. This is, you don't need very strong interaction to have this kind of phases, whereas here it's mandatory to have strong interactions. The examples of this, so the canonical one, the existing one, is fractional quantum Hall effect. Xiao Gongwen would tell you that the oldest member of this family is actually a conventional superconductor. So those are real-life superconductor. And there are also gap quantum spin liquids, but those are not very well-established experimentally. Okay, so maybe I should wrap up. So I have three main messages that I can repeat. I already mentioned. Yeah, sorry.
So are you claiming that a BCS superconductor like aluminum or lead is a topologically ordered state of matter?
Yes.
I think that's a very controversial statement, and there is recent work by the Harvard group, Vishwanath, Bongren, and Verison, which claim that actually it should be thought of as an SPT phase rather than as a topologically ordered phase. So this is certainly something that the experts do not agree on.
It's a very old statement, actually. It goes back to 91.
Sure, no, it's an old statement. There's a paper of Sondi and collaborators. But just because it's old doesn't mean it's true.
Yeah, I agree.
Just to make sure, so this is in 2D. I mean, like aluminum, it has to be 2D to have this topologic.
No, in principle, it's also true in 3D. So in 3D, the subtlety is that the anions, they need to be line-like objects. But in a conventional superconductor, the vortex is a line object, actually. It's one-dimensional. It's a flux tube. So conventional superconductor in 3D, it's supposed to be to belong to this family. But the statement, it's in my opinion, the important statement is you are here when you consider a superconductor, you're not really paying attention to vortices and to the coupling to the electromagnetic field. And when you say gauging,
that's not what the Harvard group says. We can discuss this.
Yeah, sure.
With dynamical gauge fields, it's in the SPT.
Okay.
I can give you the reference.
I didn't follow the most recent, but let me just say that because it's recent doesn't mean it's true either.
Even I agree. I actually don't believe either. Okay. But I'm just saying it's very controversial. It's very important that to students we don't say certain things which are controversial. That's all.
Okay. Yeah, to me this is okay. I thought it was well established, but maybe not. So maybe the 3 points I want to emphasize to conclude. Yeah, first remember that Majorana fermions are not the same as Majorana zero nodes. Maybe this I made the point. Yeah, but I had like this distinction between topological bands and topological order. To me, this is really so. There are connections between the two families, obviously, because here you have superconductors on both sides. But here, the case we saw, there was the classification with the Z. And inside this Z classification, we saw that once we take the vortices seriously, there is a 16-fold sub-classification. Yeah, okay, maybe I only have those other 2 points to make. Okay, so let me stop here. Yes?
Allowed that?
Yeah.
Just a very obvious question. So you made this Z2 distinction between odd and even integer numbers, superconductors, where the even ones, they don't have the protected Majorana bound state in the vortex. But they still are anions. So that's my sort of question. So if nu is even, the vortex itself is still a non-trivial anion, even though there is no protected Majorana bound field inside.
Yeah, but it's first it's a abelian case, so they don't have the property that you are splitting an internal space in 2 spatial locations. And the other thing is that the E and the M by themselves they are not very anionic in the sense that their self-statistics is bosonic, and the only thing that reveals that there are anionic behavior is when you braid one with the other. So it's not really the vortex by itself. It's the way it talks to the fermions that reveals something non-trivial.
But then in the nu even class, the d sigma is not square root of 2.
So there is no d sigma in that case, because now I have instead of d sigma, I have a dE and a dm, and they are equal to 1. They have no internal state. So the big difference is that in one case, there is a single type of vortex, and you need two vortex to code for a two-dimensional space. That's the case of Majorana zero mode. In the other case, a single vortex already has a two-dimensional complex space, and it can be empty or occupied, but it doesn't need a partner.
I understand. But that's the toric code is for nu equals 0.
Yes.
But then what's for even? So nu equal 2, 4, 6, 8.
Yes, so I didn't mention actually. So this one is more or less the prototype for all the odd case. So those are all the odd case mod 16. This one is the prototype for nu equals 0, plus minus 4, and 8. And then there is another family which is nu equal plus minus 2 plus minus 6. And then it's another theory which is called Z4. It also has two type of vortices, but they have a slightly different physical interpretation. So the toric code like only exhausts half of the even cases.
Other questions? So the Majorana H mode, it does not carry any charge.
No.
It only carries the heat.
Yes.
So this chiral means the heat flows this way.
Yes. Yes. And to my knowledge, this has been measured by Vitaly Banerjee and the group of Bloom. But in the case of fractional quantum Hall effect at nu equal 5/2, that is supposed to be via some complicated transformation a P plus IP superconductor. And what's striking there is that the heat transported, if it's really by the edge mode, it should be half what you expect from a charge mode, if it was an edge of an integer quantum Hall effect.
Next question, maybe? Don't be shy. Okay, if not, we can thanks again, John Noel.